Okay. I'm sorry about last week. I was feeling kind of sick after getting a flu shot, so I didn't want to have a lesson last week, but this week I'm better, so that's good. I guess I could start now. Let me record. Oh, I am recording. Okay. So hello, everyone. Welcome to the next lesson, lesson 12. Today, we're going to be talking about grams. We're going to continue stoichiometry, which is a fancy term for our math calculations. And today, we're going to learn the whole picture of a long stoichiometry problem, and we should be able to convert grams to grams today. So for this week, there are 4 questions in a Google Forms quiz that I have already posted. And I'll give you written feedback as always. And if you have any questions about the homework or if you're stuck, feel free to email me. I'll post this PowerPoint at jasonzhang@alphademic.org. So today we're going to do empirical formula review, since I realize that's a topic that a lot of people struggled with on the homework. And then we're going to do what I planned for today, which is grams to grams conversions. Okay, so empirical formulas, we basically need percent to understand what percent composition is. So the percent composition of a compound leads us to deriving its empirical formula. And the empirical formula, remember, is the formula with the smallest integer subscripts. So for example, like, I think I did list some examples. H2O. H2O has the empirical formula H2O. It's the simplest formula because it's a 2-to-1 ratio. Let me see if I could write. Okay. It's a 2 hydrogen to 1 oxygen ratio. There's no way we could simplify it anymore. So that is the empirical formula. On the other hand, H2O2, if we can see, it is 2 hydrogen and 2 oxygen. Notice that we could divide everything by 2 and get 1 hydrogen to 1 oxygen. So we can simplify it. So this is the empirical formula HO. And the final one, C6H12O6. Let's look at that more in depth. Okay, so it's carbon to H to O. It's 6 to 12 to 6. We want to see if there's any factor that can divide all of these terms. And we know it's 6. So we could divide each term by 6. So we can get our simplified ratio of 1 to 2 to 1. And that's how we get our final empirical formula, CH2O. We divide everything by 6, and that gets our desired answer. Okay? So that's empirical formula and percent composition. So I want to start with this example problem. A compound consists of only nitrogen and oxygen, and we determine it's 0.483 grams of nitrogen and 1.104 grams of oxygen. So find the empirical formula. So please type in the answer into the chat, and as a and remember, the first step we need to do is convert grams to moles. So why don't you everyone just do this step, and please type in your answer to the chat. So the question I'm asking is, how many moles of nitrogen are there and how many moles of oxygen are there? Oh, wait, sorry. Remember, to convert grams to moles, we use the molar mass, right here, and right here. So we can use 16 for oxygen and 14 for nitrogen. Okay, so everyone did a good job. So remember, we have 0.483 grams of nitrogen. And by the molar mass, we have 14 grams per 1 mole. So we put that into our calculator. I don't have it calculated, so I'm going to calculate it right now. We get 0.0345 grams of nitrogen. So that's what I was asking. And similarly, we can do the exact same thing for the other one. So sorry, that's too big. 1.104 grams of oxygen. The molar mass is 16, so 16 grams per 1 mole. And we put that into our calculator. And we get the value of 0.069. Oh, sorry, this is a mole, sorry. Mole of oxygen. So that's how we do the first step. We convert all the grams into moles. So, yep, everyone who answered did a great job. So that's step 1 to finding the empirical formula. Step 2, so that's what we got. Step 2 is divide the moles by the smaller number. So we can easily see that 0.0345 is the smaller number. So we divide by 0.0345. So once we do that, we get nitrogen to oxygen. Nitrogen gets a 1 and oxygen gets a 2. So we're almost done. Then we need one more step. Make sure the subscripts are in the simplest form. There's nothing that divides 1. There's no GC, greatest common factor, that divides both into 1 and 2 other than 1. So it is the simplest form. So we just use them as subscripts. Whoopsie, sorry. Let me annotate. So then our answer is, we just use these numbers as subscripts. So NO2, and that's our final answer. So by knowing how many grams of nitrogen and oxygen, we could find the empirical formula. Yep. Someone asked, they have to be relatively prime factors. Not necessarily. They could be oh, yes. Yeah, that's true. They do. The numbers have to be relatively prime for us to accept it. So that's how we do one of these problems. So as a review, we convert all the grams we have into moles. We divide the moles by the smaller number, and we make the subscript as the empirical formula. So I'll let you guys try it. I'll give you like 2-3 minutes. So a sample contains 6 grams of carbon and 16 grams of oxygen. What is the empirical formula? So use 12 for the molar mass for carbon and 16 for the molar mass of oxygen. And type in your answer in the chat when you have it done. If you don't understand or need help, feel free to just contact me, ask a question in the chat, and I'll try to help you through the problem. So let me write the steps on the board so everyone can at least so step 1, convert grams to moles. Step 2, divide by smallest number. And step 3, we put an empirical formula. So you first need to do step 1, then step 2, then step 3. So that's how you always solve these calculations. I'll give you another minute or so. Okay. So I'll start. We need to first convert grams to moles. So 6 grams, the molar mass is 12 grams per mole. That's what the 12 is. And as usual, we can cancel out the grams. So we can get 0.5 mole of carbon. And similarly, 16 grams of oxygen. So 16 grams oxygen, 1 mole. We notice that the grams of oxygen cancels on the top and bottom, and we're left with 1 mole of oxygen. That's step 1. Step 2, we divide by the smallest number. So we divide 0.5. So we get carbon to oxygen. Carbon is 0.5 over 0.5, which is 1. Oxygen is 1 divided by 0.5, which is 2. So that's what we get after step 2. And step 3, we put it into the empirical formula, C1O2. But always we don't put subscript when it's 1. So it's just CO2, carbon dioxide. And that is our answer. So good job to everyone who got it right. A lot of you did. So that's how these problems are, the 3-step problems. Let's try another one. A sample contains 12 grams of carbon, 2 grams of hydrogen, and 16 grams of oxygen. What is the empirical formula? Use 1, 12, and 16 for the molar masses. Some of you guys are really quick. So I'm going to just write out the steps again. Step 2, divide. barely even a step, empirical formula. Okay, so our first step is grams to moles, so 12 grams carbon. We look at the molar mass, 12 grams, 1 mole. So that's just 1 mole carbon, which is fairly simple. For the hydrogen, 2 grams of hydrogen, the molar mass is 1. So 1 gram hydrogen, 1 mole of hydrogen. That's 2 moles of hydrogen. And remember, moles are just a defined quantity. And the last one is 16 grams of oxygen. And the molar mass is indeed 16 grams of oxygen. So this, oxygen, sorry, 1 mole of oxygen. So that's step 1. Now we go to step 2 and we divide by the smallest number. We see that 1 and 1, that's the smallest number. So we divide by 1. So CH, 1, 2, 1. We divide by 1, which does nothing. And then step 3, we use these coefficients in our empirical formula. So CH2O is your answer. So good job to everyone who attempted this problem. They all got it. You guys all got it right. So here's a special condition if it doesn't work out for us. So what if we get like fractional numbers for step 3 when we divide stuff out? So our solution is we multiply all numbers. We multiply all numbers by constant until they're all integers. So for example, if you get 1.00 and 1.67, if you try out some numbers, you realize 1.67 is really close to 5/3. So why don't we multiply each number by 3? So we get carbon to hydrogen is 3. 1 times 3 is 3, and 1.67 times 3, that's like 5.01, which is really close to 5. So we could just assume that's 5 because it's just so close and it might be due to experimental errors. So then the empirical formula will be C3H5. So that's how we do it if we have fractional numbers. We multiply it by a constant and we get whole numbers. But like if something is like you get 0.99C and 1.00H, 0.99 is so close to 1, you could basically just assume it's calculation errors or experimental errors, and you could just round it up if it's close. So it doesn't have to be exactly 1. As long as it's close enough, we can assume it to be the nearest whole integer. So here's another example that we're gonna do. Carbon 1, oxygen 2, nitrogen 1.33. So the carbon and oxygen are fine, they're whole numbers, but the nitrogen, it's not close enough where we could round. So if you know a little math, you realize this is approximately 4/3. So if we multiply everything by 3 again, we get carbon, oxygen, nitrogen. Carbon 1 times 3 is 3. Oxygen 2 times 3 is 6. Nitrogen 1.33 times 3 is 3.99, which is close enough to 4. And then we could just do C3O6 and 4. And that's our empirical formula. We do not do C1O2 in 1.33 since we cannot have these fractional atoms. Like, what does it mean if you have 1.33 of a nitrogen atom? We don't know, so we have to use whole numbers. And here's an example where we're actually going to use what we just learned. So it's the same thing, except this time in step 3, you're going to get fractional numbers, and you're going to have to do what I just taught you to clear away those fractions. So the question is, a sample contains 14 grams of nitrogen and 24 grams of oxygen. What is the empirical formula of this compound? The molar mass of nitrogen and oxygen is 14 grams per mole and 16 grams per mole respectively. So you might be like a little confused, but the steps, step 1 and step 2 and step 3 are the same. So step 1 is grams to moles, because we need mole comparison for the empirical formula. Step 2 is divide by smallest moles. Three is use empirical formula. So I'm gonna give you guys 2 minutes to do this problem. And if you need like any help, just ask me in the chat and I'll try my best to help you. If you need help at the very end or if you need help at the beginning, that's fine. So I'll give you some time to solve the problem. Just in case you're stuck, I'll do the first step for you guys, with you guys actually. So we take 14 grams of nitrogen and we use the molar mass, which is 14 grams per 1 mole. And we don't even need a calculator. We could do it in our head, 1 mole of nitrogen. Similarly, we can do oxygen, 24 grams of oxygen, 16 grams of oxygen, 1 mole oxygen. I'm like going faster on these stoichiometry steps because I feel like we're more experienced. The grams oxygen cancel out, so we get 1.5 mole oxygen. So I'll stop here and let you guys think to try to do step 2 and step 3. I'll give you like 30 seconds. So dividing by the smallest number. And then in step 3, what I said about making, after you divide by the smallest number, making everything a whole number. Okay. So I hope you realize that the smallest number is 1. So we divide by 1, which does nothing. So we get NO, N is 1, O is 1.5. But here's a problem. We can't have 1.5 oxygen atoms. So what we're gonna have to do is multiply by the smallest number. That makes every number whole. So multiplying by 1 doesn't work. So let's try multiplying by 2. So 2 times 1 is 2 for nitrogen, and 1.5 times 2 is 3 for oxygen. Yep, it works since they're both whole numbers. So now we can put it into the empirical formula N2O3. And that is indeed our answer. So this is just a 3-step problem, and that's how we do all 3 steps. The first step, grams to moles, then we divide by the smallest number of moles, and then we use empirical formulas to make it the whole numbers. So I have one last problem today on this it's similar. So a compound has 18 grams of carbon and 24 grams of oxygen. What is the empirical formula? And the molar mass is 12 and 16 respectively. So I'll give you 1.5 minutes to think. Remember, step 1 is grams to moles. Step 2 is divide by smallest number. 3 is use empirical formula and get whole numbers. Okay, I'll get started now. So we start with the grams. So we have 18 grams of carbon and we have 24 grams of oxygen. We use the molar mass. Carbon is 12 grams per mole. And oxygen is 16 grams per 1 mole. I'm sorry for my bad handwriting today. But I'm using a pen today, so it's faster but sloppier. So 18 divided by 12 is 1.5 moles of carbon, and 24 divided by 16 is 1.5 moles of oxygen. So we're done with step 1. So step 2, divide by the smallest number, 1.5 and 1.5. So we're going to divide by 1.5. So we get carbon to oxygen is 1 to 1. And they're both whole numbers, so we're happy. So we're going to put that in our empirical formula, which is CO. So this sample is CO. So everyone did well. So now we're going to do what we're going to cover today. I hope everyone understands empirical formulas a little better, at least. And there's one homework problem on empirical formulas. But now we're going to do grams to grams conversion. So let's review what a balanced chemical equation is. It gives the mole ratio. So one example is water turning to hydrogen gas plus oxygen gas. So that's not really likely. You actually need lots of energy to make this reaction occur. But notice that the coefficients, which I'll underline 2, 2, and it's implied a 1, that gives us the molar ratio between any two reactants. So if we want to do water to hydrogen gas, it's 2 moles of H2O equals 2 mole of H2. So that means for every 2 moles of water we have in the beginning, we're going to get out 2 moles of hydrogen gas at the end. And we know we could divide since they're both divisible by 2. So we can divide by 2. So we get 1 mole of water equals 1 mole of hydrogen gas. Similarly, we can do the same thing for H2O and O2. So we have 2 mole H2O equals 1 mole O2. And as you can see, we can divide. There's no factors that we can divide between the 2 and 1. So that's our simplest form. So that gives us the mole-to-mole ratio. So now let's review mole-to-mole conversion. So lithium metal explodes with this following equation. 2 lithium plus 2 water yields 2 lithium hydroxide and 1 mole of H2. So please type in your answer in the chat. We're going to go a little faster on these. So if 6 moles of lithium react with 6 moles of water, how many moles of hydrogen gas are formed? So this is basically just a proportion. So we're basically looking at the proportion between lithium and hydrogen gas, which we use the coefficients to find the molar ratio. So it's a 2 to 1. Well, it's implied as a 1, since if there's no leading coefficient, it's always a 1 as implied. So let's start. So we start with 6 moles of lithium. So by the balanced equation, we know that 2 moles of lithium equals 1 mole of H2. That's an equality. So we can divide both sides by 2 moles of lithium. So we can get 1 equals 1 mole H2 over 2 moles of lithium. And now this is a conversion factor that we can use. 1 equals 1 mole of H2 over 2 moles of lithium. We can use this conversion factor up here. So we're going to multiply both sides by 1 mole hydrogen over 2 mole of lithium. So as you can see, the moles of lithium cancel out, and we get 6 over 2, which is 3 moles of hydrogen. So that's how we get our answer of 3. You can also think about it logically. So it's a 2 to 1 ratio for lithium to hydrogen gas, and we have 6 moles of lithium. So we're multiplying by 3 here. So we're going to have to multiply by 3 here. So we get 3 moles of hydrogen gas as well. So there's 2 ways of doing it. Okay, so here's one more question. Please type in your answer in the chat when you have it. So it's 5 moles of H2O formed. How many moles of lithium are needed? So it's a similar problem type. Oh yeah, we're reviewing this. So because we're going to need this for our long calculation of grams to grams. So let me do the simplest way first, and then we can do the longer way later. So the ratio of lithium to hydrogen gas is 2 to 1, like we know above. Now we know 5 moles here, and we want to know how many lithium here. We're multiplying 5 from 1 to 5, so we're going to have to multiply 5 here. So 2 times 5 equals 10. So that's one way. Another way is we start off with 5 moles of H2. By our balance equation, we get 2 moles of lithium equals 1 mole of hydrogen 2. Since we want to get rid of, cancel out the moles of hydrogen 2, we want moles of hydrogen 2 to be on the denominator. So to get our conversion factor, we divide by moles of hydrogen 2. We could just treat them like a fraction. So we get 1 equals 2 mole lithium over 1 mole H2. We're basically just dividing moles of H2 on both sides, and we could use that as a conversion factor. So we multiply it with our 5 moles of H2. We cancel out that. So we're left with 5 times 2 is 10 moles of lithium. So that 2 approaches gave us the exact same answer. So now our last thing we need to review is moles to grams, and then we could piece together everything that we've learned. So how many moles are in 10 grams of N2? The molar mass of N2 is 28 grams per mole. So please type in your answer in the chat when you've got this problem, the answer. You could give your answer as a fraction, decimal, it really doesn't matter to me. Oh, sorry about that. This is honestly just a conversion factor, stoichiometry problem, whatever you like to call it. So we always start with what we have. We have 10 grams of N2. But what do we want? We want moles. And the only way we could get from grams to moles is molar mass. So we want to multiply by that constant. But do we want the 28 grams on the top or the bottom? Since we want to cancel out grams, we want the 28 grams N2 to be on the bottom, so we could cancel it out, and 1 mole of N2 on the top. So since we're multiplying, we know that the grams of N2 cancels out with the grams of N2. So we have, it's 10 over 28, which is about 0.36. So that's our answer. So it is like 0.36 moles of N2. So this is fairly simple to convert from grams to moles. We just multiply by the molar mass. Yep, 0.357, yep. And now let's do the reverse. So how many grams are in 0.357 moles of N2? The molar mass is still 28 grams per mole. I realized I switched the title on top. It should be moles to grams, and the last one should have been grams to moles, but I'm sorry about that. I've switched the order. Whoops. Okay, we learned this in the past, I think 3 lessons ago. Then we're going to start with what we have, 0.357 moles of N2. We're going to use molar mass just like the last problem. But this time, we're going to put the moles on the bottom so we can cancel out moles of N2. So we multiply by 28 grams of N2 over 1 mole of N2. And like last time, we could cancel out the moles of N2. So once we plug that into our calculator, we get around like 10 grams of N2. So this was basically the last problem just in reverse. So we converted grams to moles, and now we converted moles to grams. Yep. So now let's piece everything together. I think all we have time for today is one guided problem, maybe one more problem, but I'm not sure. So let's go through one of these long problems that take some time. So suppose we have in this reaction, hydrogen gas plus oxygen gas equals water. This is actually occurs pretty rapidly. It's spontaneous, so that means it occurs without input of energy. So suppose we have 4 grams of hydrogen gas. So how many grams of water are formed after we react hydrogen gas with excess oxygen? So this is a multi-step problem. So we start off with 4 grams of hydrogen, and we want to know how many grams of water there are. So I break it up into 3 steps. The first step is convert grams to moles. Because balanced equation, we can only convert between moles to moles. We can't convert grams in the balanced equation. So here's a misconception I see a lot of people do. They looked at the balanced equation and they assume it's like 1 gram of hydrogen equals 2 grams of water. This is completely incorrect. The only thing we have from the balanced equation is we have 1 mole of hydrogen gas to 2 moles of water. By definition, the coefficients tell us the molar ratios. So it's not the grams, it's the moles. So that's why when we get grams, we want to convert it to moles automatically. If you do any stoichiometry problem, chances are you're going to be converting it to moles, because moles are the basis of all chemistry calculation in stoichiometry. So what we do is we do 4 grams of hydrogen gas. We use the molar mass, which is 2. Because hydrogen is 1, but we have 2 hydrogen in hydrogen gas, so it's 2 grams per 1 mole. So we get 2 moles of H2. And the reason we multiply it in that order is, as always, we want to cancel out the grams. So the only unit left is moles, and that's the unit we have that we want. We want to convert grams to moles. So once we have 2 moles of H2, we can use the balancing coefficients to get the number of moles of water, which would be on the next page. Like I said, 4 grams of H2 is 2 moles of water. So our next thing we have to do is convert moles to moles using the balanced equation. So what I just said is the molar ratio. It's a 1 to 2. So we know that we have 1 mole of hydrogen gas, and that equals 2 moles of water. So we know we have 2 moles of H2 from the last equation. But now what we want is we want to convert the moles to moles of hydrogen to moles of oxygen. So we know that hydrogen gas to water is 1 to 2, and we have 2 moles of hydrogen. So how many moles of water do we have? We know that we multiply 2 to get from 1 to 2, so we're going to have to multiply 2 on the other side. So 2 times 2 is 4. So we know we have 4 moles of water. So that's step 2. We converted moles of hydrogen to equal 4 moles of water. And that's exactly what I did. And the last step is the easy step. So we have 4 moles of water. We want to convert moles to grams. And the only way to do that is molar mass. So 4 moles of water. The molar mass of water, hydrogens are 1 and oxygens are 16, but we have 2 hydrogens and 1 oxygen. So 1 times 2 plus 16, that's 18. And we want the grams to be on the top, 18 grams per 1 mole. So we can cancel out the moles. So the mole of H2O and the mole of H2O cancel out. So the only unit left we have is grams of water, which is exactly what we got. 4 times 18 is 72, I believe. Let's see the answer key. Oh, wait. I made a mistake on the answer key. It should be 72. I think I divided instead of multiplied.
Yeah, you probably divided. 0.2 is close to 4 out of 18.
Yeah, I'm sorry about that. The answer key is wrong. You actually multiply by 18 and get 72. It is not, let me go back. It is not 0.2. That's a mistake on my part. I'm sorry. So this is wrong. I'll change that before I post it. It's 72 grams of water. So if we start out with 4 grams of hydrogen, we're going to end up with 72 grams of water if everything goes to completion. So that's a gram to gram conversion. So let's review the steps. So we first get out, we have grams in the beginning. Since the balanced equation only gives mole ratio, we all need to convert grams to moles. And then we use the balanced equation to convert moles to moles. And then we finally convert the moles to grams at the very end. I think for the homework problems this week, I don't have you guys do a whole calculation, but each individual step, there's like 1 question. So from converting grams to moles, you have a question. Converting moles to moles, you have a question. And converting moles to grams, you have a question. So I'm like building you guys up. And next week, we're definitely going to do a lot more of these. So I think we're going to end with this problem. This would be our last problem today. So it's the same equation, but we have 32 grams of oxygen. So please type in your answer in the chat when you're done. So how many grams of water do we have after reacting with excess hydrogen gas? So last question, we had excess oxygen and we had a certain amount of hydrogen. This time we're reversing it. Let me give you the molar masses real quick. The molar masses for hydrogen, oxygen 2, that is 32. And the molar mass for water is 18, I believe. I know this process may be hard, but chemistry, or at least introductory chemistry, has lots of math. So let me repeat the steps. Step 1, grams of oxygen to moles of oxygen. So we could use the balance coefficients to get moles of oxygen to moles of water. And then finally, from moles of water, we can get to grams of water by the molar mass. So these two are the 2 important molar masses you need. So it's grams per mole, and it's 18 grams per mole as well. I know some people are extremely speedy, and I've already finished this problem. I'll give you guys like one to 2 more minutes since this one's a little longer. Sorry for keeping you guys over today. We just have a lot of content in this lecture, and it's somewhat challenging. Okay, I'll start with the first step to get you guys started. So we have 32 grams of oxygen. We want moles of oxygen so we can convert from oxygen to water. So we use the molar mass. I've said right there 32 grams of oxygen, which is 1 mole of oxygen. And we cancel out the grams of oxygen. So we get 32 divided by 32 is 1 mole of oxygen. So that's step 1. We converted grams to moles. Okay, so now let's do the second step, which I'll have in a different color. So we look at moles of oxygen and moles of water. It's O2 to water. It's 1 to 2. We know that we have 1 mole of oxygen, so 2 moles of water. It's just a multiply by 1. So we know we have 2 mole of water. Now the last step is quite simple. All we have to do is use the molar mass. And this time we want the moles to be on the bottom since we can cancel out the moles. So 18 grams of water over 1 mole of water. And we can cancel out the moles. 2 times 18 is 36 grams of water. So I think like a common mistake in this problem is that you didn't see O2. There's a subscript 2 down here, and you probably did 16 grams O2 in step 1 instead of 32 grams of O2. We don't want the moles of oxygen. We want the moles of oxygen gas, since that is what we're reacting. We don't care about the moles of oxygen. We only care about the moles of oxygen gas. And it's the moles of oxygen gas that gives us the balanced equation. So I'm sorry for keeping you guys over today. So our review is we reviewed empirical formulas. So we have like 8 grams of this substance, 9 grams of another. We know how to find the formula from it. And we did the tedious conversion from grams to grams. So we start off with like grams on the reactants. We convert the grams of reactants to moles of the reactants, moles of reactants to moles of products, and then moles of products to grams of products. We did 2 examples in class. There's going to be 4 homework questions in the Google form quiz. I know some of you guys already done it. I would highly recommend you to do it. And I'll give written feedback and post your grade. And if you have any questions, please, or about homework or anything, please just contact me. Thank you guys.
You divided on the answer key to the other problem too.
Oh, I did? Oh, I'm sorry. I'll fix that.
I saw.
Yeah, I'll fix that before I post it.
Okay, thanks. Bye.
Thanks. Bye.